This is Sung, and I'm the Principal and Director of Sky Academy. And let me tell you, in this episode, I'm really excited. I'm excited because we're going to, in this episode, do a number of things. We're going to take all the work that we've done on calculus, yes, the work on differentiation, the work on integration, the work on applying geometrical applications of calculus, remember those? That unit of work. And I'm also going to take the other unit that we did on indices and logarithms, right? And the work that we did using index laws and log laws, and I'm going to marry it all together, mash it all together, and we're going to apply calculus to exponential functions, okay? And the purpose of this episode, the intention of this episode, is to analyze an exponential graph and basically look at what will happen if we try to differentiate it, okay? So that's the intention for this episode. So let's have a look at what an exponential graph looks like. So for example, consider the function, or a function, y equals to a of x. So y equals to a of x will look like this, remember? All right? So basically, as x gets more and more negative, what happens is the graph will approach zero as x gets more and more negative. So the graph, or the y value for the graph will approach zero, but as x gets bigger and bigger, the y value will shoot off into infinity, yes? So as x gets infinitely large, y gets infinitely large at a faster rate, in essence, okay? And the number a, right, will just tell us how steep this curve goes or not, okay? So the smaller a is, the less steep it is. The bigger a is, the more steep it is, okay? So that's basically what an exponential graph looks like, right? And let me now, on the other side, look at what calculus does, and in particular differentiation. When we're differentiating a graph, what are we doing? We are actually looking for the gradient function, or the gradient rule that gives us the gradient at any specific point, okay, of the tangent of a curve. All right, so the tangent of a curve is basically a line that represents the gradient at a specific point. It's a line that touches the curve at that point, but doesn't cross it. Okay, so it has, so for example, at this point here, right, the gradient will, the tangent will represent, all right, the gradient of the tangent will represent the gradient of the curve as well. So for example, at that point here, the tangent looks something like this, right, at that particular point, right, of x. So let's call that x1, all right? The gradient of that line will represent the gradient of the whole curve. Yes, because it's the gradient of the tangent. And the way you get the gradient of that line is you got to work out the gradient rule, and you work out the gradient rule by differentiating this. Yes? All right? So basically, the derivative of a curve represents the gradient. Okay? So let's have a look, and I've basically done a little table, right, which we're going to use to analyze what's going on in this particular graph. Okay, so let me start by saying this. For y, so in other words, for the y value, or the vertical value, the vertical displacement of this graph, the higher y is on the graph, so the higher y is on the graph, all right, the bigger f of x is, because the function f of x represents the height of the graph as x moves across. Does that make sense? And for y dash, in other words, the derivative of y, the steeper the gradient of f of x, the steeper the gradient is, the bigger f dash of x is. Okay? So let's have a look. Let's have a look in particular at y equals to f of x. So in other words, the function. Okay? Now, as x approaches positive infinity, so in other words, as x gets really, really, really big for this function, what's happening to the height of this function? The height of this function is increasing. Do you see that? So as x gets really, really big, in other words, as my ruler goes to the right, the curve is getting bigger and bigger and bigger and bigger. So as x approaches infinity, f of x, the value of the function, is also approaching positive infinity. See how it's getting bigger? Yeah. Now, as x gets bigger and bigger, let's have a look at what f dash of x does. In other words, what's the gradient of the tangent doing? Well, it starts off flat. See, as my finger moves across to the right, let's see what the gradient's doing. All right? The ruler represents the steepness of the curve. All right? And what's happening to the ruler? It's getting more and more vertical. Do you see that? It's getting more and more vertical, and the steeper or the more vertical the graph becomes, the bigger f dash of x. Now, what is the gradient of a vertical graph? Or what is the gradient of a vertical line? The gradient of a vertical line approaches infinity, okay? Because the gradient represents the rise over the run, and the run on the bottom is 0. When you divide any number by 0, it's undefined. It becomes infinite. It approaches infinity, right? So in other words, what's happening to f dash of x? What's happening to the steepness of the curve? It is also approaching infinity, okay? It's also approaching a positively infinite value, okay? What's happening as x gets smaller and smaller? So in other words, as x approaches 0, as x approaches 0, f dash of x, or the function, approaches 1, and as x goes towards negative infinity, as it gets more and more negative, what's happening to the function is it's getting smaller and smaller and smaller, but it will always remain positive. It won't actually go below the x-axis. It'll approach the x-axis, but will never touch or cross it. Okay, so the x-axis is what we call an asymptote. Yes? So if the x-axis is an asymptote, what does the height of the graph approach? The height of the graph approaches 0 from above. Do you see that? It approaches 0 from above. And what is happening to the gradient of the function? As my finger goes more and more right, what's happening to the gradient of the function? It's getting flatter and flatter. Do you see that? And what is the gradient of a really flat or horizontal line? Okay, the gradient of a horizontal line is 0, and it's going 0 from a positive steepness, because this is a positive steepness, this is a negative gradient. Okay, so as x approaches negative infinity, as x gets more and more negative, the gradient of the function will also approach 0 from above. Okay? Now, why did we go through this exercise? We went through this exercise basically because I wanted you to notice that the function, the gradient of the function, will emulate, will mirror image, will copy what the function is doing. Do you see that? So what does that suggest? It suggests that the gradient function of a graph, in other words, the first derivative of an exponential graph, will be another exponential graph similar to the original function. Okay? So in other words, when you differentiate an exponential function, you should get another exponential function. Okay? What I can say is it's basically like this. F dash of x will be proportional, all right, to the original graph. And what that means is f dash of x will equal to the original graph times some constant. Okay, so that's what I want you to notice, that when you differentiate an exponential graph, you get another exponential graph that appears to be proportional to the first. Okay, good. Alright, so basically what I want to do now is give you that in words. To sum up this episode altogether, this is what I'm going to say, right? The derivative of an exponential function will give another function that is proportional to the original function, alright? That, for now, for the time being, appears to be the case, right? In the next episode, we will prove it to be the case by applying differentiation by first principles to exponential graphs, okay? So just take that all in. Thank you very much for watching.